I want to talk about the presentation by Subhasish Mitra. He's a professor EE at Stanford, and it's about nanometer scale compute technology. So I think Mitra's presentation was inspiring in several ways. First, kudos to him for really exciting his work, but it's by no means the kind of work where a broad audience gets excited. It's hardcore engineering, detailed technical stuff, IEEE type stuff, IEEE stuff, where unless you're in the field, you might not even understand what's going on. But nevertheless, he's one of those types that can bridge, I think, the gap, at least to an audience which is, like us, interested, knowledge hungry, investors, application type people, business people. And the reason it's exciting is because I feel like the field of computer architecture and chip design really is going through a renaissance. This goes way back to Onur Mutlu and his lectures that we attended years ago, the lectures that were online from CMU and then later on from the Polytech in Zurich. And I think this is sort of the next level here because what Professor Mitra is talking about now is a whole new, let's call it a manifesto towards a new compute architecture that deals with the requirements of AI. Now, what are the requirements of AI? Let me start with, there's a couple of papers, links are in the show notes. One is about moonshots, and one is like a virtual model for the world. I think this is a beautiful way to express the purpose of this whole work, right? We talk a lot about AI, we talk a lot about the benefits of large language models and all that kind of stuff. And I think when we sit back a little bit and we analyze, okay, what is this actually all for? Where is this going? And what Professor Mitra and other collaborators at Stanford and also around the US, mainly, I think a couple of universities, Berkeley is definitely part of it. What they're trying to do is really build a new infrastructure that can enable a virtual model of the world, because a virtual model of the world requires really, really advanced AI. Okay, think about it, like you can simulate reality, so you can build a simulation of the reality that we probably perceive through a model in our brain. And the goal, of course, to have a virtual model of the world is to be able to iterate faster and develop technologies. There's other goals, but this is one of them, right? We can develop technologies. So we could, if you imagine if we had a virtual model of the world, we could run scenarios where we could say, okay, what kind of energy policy should we have that maybe in the next 100 years will reduce CO2 emissions, at the same time not destroy our environment and have economic growth and so on and so forth. So this is a really bold project, right? This requires a lot of compute. And that's why I think by setting this really long-term goal, this is a little bit like the Mars landing of SpaceX, right? Or the fully autonomous Cybercab for Tesla. Like, it's a long shot. It's really a moonshot in a sense that it's really hard to achieve. But on the way there, hopefully, we will get some good technology. So I want to discuss this and then go a little bit into the weeds, because what I really find most interesting is the application of nanoscale technology, carbon nanotubes, as a replication, as a replacement of current transistor technology, and then three-dimensional chips and in-memory compute. And sort of discuss a little bit what the endeavor is about from a little bit more technical perspective. This is not even on podcast. It's October 27, 2024. This is Krim Delco. For the year, we are up 34.9%. The market is up 21.8%. We're outperforming by 13.1%. The main driver of our outperformance is the recent performance of Tesla, but actually for the year, the main driver of the outperformance is NVIDIA. So let's talk about Professor Mitra's presentation, which was in the context of a lecture that he gave recently at Stanford. I think I want to focus on the moonshot. I really find this inspiring because once you have a purpose, okay, we want to build a virtual representation of the world. By the way, the moonshot number 2 would be to have an interface with this virtual world, whether this is a 3D headset or a Neuralink type device. That remains to be seen, but that's the second moonshot. I want to focus on the first one. So what is moonshot number 1? A virtual model of the world. Achieving this moonshot will require breakthroughs on many fronts, including nanometer scale components, innovative logic and memory integration, advanced in-packaging and interconnects, mixtures of photonics and electronics, and entirely new chip architectures to implement the next generation of efficient artificial intelligent algorithms. So he's really talking about the whole stack, the architecture, which is required to achieve this goal. And what is the goal? Let's go a little bit further back. Okay, if we want to have a full representation of the real world in virtual world, we need to find a way to run generative AI models at scale. And what are generative AI models? They do rely on probabilistic data analysis. So that's the first, let's say, hurdle, right? Or the first point to discuss, which is, okay, what are we talking about here? Okay, we want to build a model that represents the real world, or we want to have very advanced AI models. What we need for that is we need massive ability to analyze data in a probabilistic way. So we get a certain input and we try to assign a certain probability that this input belongs to a certain distribution. So let's say I can prompt a model and say, I want to simulate a self-driving car. Please give me a scenario where the car drives through a city and a couple of things happen and I want the car to navigate through. This is the prompt, this is the input, and then the model has to be able to assign probabilities of certain outcomes and then, generate those. So what this is in general is what they call this probabilistic compute architecture. So lots of data and probabilistic outcomes. So how do they want to solve this problem? First of all, what is the problem? Well, the problem is that our compute infrastructure so far is not really well equipped for this type of stuff. Now we have bridges. NVIDIA is basically building a gigantic bridge for this with their GPU architecture, and CUDA, the software architecture, which connects the GPU architecture with the higher level software layer and the data analysis layer of modern AI systems. But what these people want to do, again, Professor Mitra and others, the names are on the papers. The goal is to build an infrastructure from scratch. And as the quote said, this takes several, the whole stack needs to be approached. So we want to talk about the actual hardware, which is the chip, the microarchitecture, all the way down to the metal. Let's start with that. So what they're proposing is carbon nanotubes. So that this is one so-called one-dimensional material consisting of silicon atoms, and these carbon nanotubes can be used as a replacement for transistor technology. Then we have logic and memory integration. So we want to have basically more in-memory compute. What that allows is that you could have more data available for analysis at any given point in time. One of the biggest problems of current AI systems is the memory wall, which is that we have very fast compute, but the compute has to analyze massive amounts of data, and the data don't fit onto the memory that is available for compute on chip, and therefore there has to be a lot of in and out, and that is power consumption. So if we could have more in-memory compute, we could do massive amounts of parallel processing of data in real time. Advanced packaging requires mainly thermal management and also static management, voltage control. Advanced interconnects That's also a lot of thermal stuff has to be solved, and precision and static issues. Mixture of photonics and electrons. Now this goes into the realm of this even touches some of the physics stuff. Let's say the astrophysics community is trying to use incredibly fast laser wave technology for compute. So the problem with photonics versus electronics is that our current compute infrastructure is built on electronics. So even if we have photonic signals, we have to translate them into electrons. And this back and forth is inefficient, and plus electrons are slower, consume more heat, are less efficient than photonics. So if we could find better photonics solutions in the chip technology, this could be a big advantage. So new chip architectures, this sort of touches upon the concept of the microarchitecture. So what this means is that, look, if we have a chip that we know can do a lot faster processing, so we can go at much higher frequencies. Right now we're in the gigahertz space, and let's say we could go 10x or 100x, and we have a lot more data available per compute interval. We could change the microarchitecture of the chip, and then also the instruction set architecture, so we could connect the chip then with the other devices, the I/O and the storage and the arithmetic logic unit and things like that. So we could have a better holistic design, and then of course we could also expand that to the system level, and finally we could also integrate our algorithms better with the chip. So what these people are projecting in the next program, they call it next or next project, is really a fully integrated solution. But what I find most interesting here, what sparked my interest, is really the nano-based transistor. So the carbon nanotube transistor consists of a new type of material that is being researched extensively in the physics department. So we have a decent amount of knowledge about how these things behave. What we don't know is how to integrate them into functioning chips. Of course, we also don't have a lot of information right now about, let's say, scalability and commercial applications and things like that. But I want to lean back for a second and just say, we talk a lot about, let's say, companies like Intel and Fairchild Semiconductor, even before Intel, when they got founded, or even Intel more recently, recently relative to Fairchild. And we talk about how they got founded and how trillions of dollars of market cap were created. And I just want to sort of lean back a little bit and just remind people, we could have another NVIDIA being created right now, another Fairchild, or maybe a couple of them. In other words, because we are at this crossroads, and because there is this need, this problem to solve for new types of compute problems, there could also be new innovation. The same way, look, NVIDIA was founded because the graphics industry required better solutions. Even before NVIDIA, there was silicon graphics. Certain solutions were created to solve certain problems, which back then, let's say, were used in the video game space, and then later on in things like Pixar, and then we went from there all the way to Sora and all kinds of very fancy, very, very high, cutting edge computer vision video applications that we live in today. So I think we could have, I guess the potential is there for a new type of computer architecture with new ideas and new hardware and software solutions that could be potentially incredibly wealth creating. Just as a side note, in one of the papers, they mentioned two important things to drive this industry. One is rapid prototyping. So we need to find a way to rapidly prototype. And the other is advanced high throughput metrology that provide rapid, high quality data that further enhance the learning available for virtual models. So what that means is, look, you can have, let's say, you need to find ways to look at the chip technology that you have in the lab and see why it might have problems and quickly iterate around those problems. So metrology is kind of the way to see, right? A better way to measure stuff. And we need to have a sort of a holistic approach towards this engineering problem, which is we don't just want to build better chips, we also want to build better instruments to measure those chips and evaluate those chips. Even the evaluation metrics themselves, right? The kinds of benchmarks that are used right now, even there I could see new types of innovations, because fundamentally, the fundamental idea behind all of these things is that we're looking at probabilistic compute. This is the fundamental. By the way, just as a side note, I asked Professor Mitra, look, we have probabilistic compute that doesn't require a lot of precision. So can we therefore also be a bit lenient with the bug problem of our hardware? So maybe it doesn't have to be as precise. He said, no. The hardware has to be precise because we always want to know whether problems that occur within the AI inference, are they based on the training of the model or the inference model, and are they based on hardware problems or architecture problems or data problems? So we need to have deterministic hardware and software so we know whether our models are correct and whether our data input is correct. Okay, you can't have good input and then bad output and then analyze why the output is bad if you're not sure that the processing technology itself is 100%. So that, I think that was a very good answer. So to summarize, look, I could go on with this. I don't want to go too long. I just wanted to mention this presentation by Professor Mitra. And we definitely are at the crossroads here of a new type of architecture. And there's a couple of things coming together: new materials, nanomaterials, new memory technologies that can be used for on-chip memory technologies, new chip design technologies, 3D chip, where we can have more compute and more memory on chip and better interconnects. And then we can embed all of this into a better all-over system design and better algorithms to solve the fundamental problem of AI algorithms, which is probabilistic compute. How the algorithms themselves will potentially change, but the fundamental idea that we want to be able to train models to create massive amounts of knowledge about how data relates to each other. And then when we do inference, we want to be able to infer from the from the input where the potential predict basically where this input belongs to, and then generate AI models based on that. I think the purpose of this podcast series is to give people a sense for what it feels like to run a hedge fund. I think this is a good example of a situation where you really want to take this very seriously. These people are, first of all, very serious engineers. And I think it also shows for some people, they might sometimes scratch their head a little bit in terms of, okay, what does a PhD in electrical engineering actually do? What does that even mean? What's the difference between electrical engineering and physics? And I think this is a good example to illustrate that difference, right? You have carbon nanotube, which are still a physics problem. We don't know exactly how these things behave. We analyze these things. We have theories about how they behave. Now we can implement them into actual systems, such as, for example, new types of transistors that then are embedded into new types of chips that are embedded into new types of systems. And we can learn from the behavior of those systems how maybe the physics can be improved and the physics can improve the systems. And we have this tandem, and that's what entrepreneurs really do, technical entrepreneurs, particularly deep tech entrepreneurs. Now, I don't know where this business stands in terms of VC funding. It seems to me it's ripe for giving it a shot. Of course, it's going up against a massive amount of investment in existing technology. But since we're hitting a wall with Moore's law, this would be a potential new avenue Again, there are other avenues, particularly, let's say, the photonic electron sort of division, which I've seen in the astrophysics community, where they have these extremely fast lasers, and they are looking at potentially using those fast lasers as direct information processing units, so we don't have to transfer the photons back into electrons. But let's stay, and there's the quantum computing side of things, of course. So there are different avenues that are all trying to open new directions and new doors for massive amounts of compute and data processing capabilities. I think what we can almost be certain is that we will actually get somewhere. Which avenue will succeed, that depends a little bit on serendipity and entrepreneurial spirit and things like that. But I think it's a very interesting and very, very promising area of research and technology and entrepreneurial opportunities. Thank you.